So we've been building up this idea of area under the curve. So we use a little geometry, we use Riemann sums, but now we want to get a little more exact with that. And where we go is to calculus. But even before we get to the calculus of it, we're going to get some notation. So our notation that we're using is for the definite integral. So the integral is this kind of curvy piece at the beginning here. And then what we can do is when it's a definite integral, what we'll be doing is we'll be stating the interval that we're taking the integral over. So in this case, it's going from A to B. So what this tells me is I'm taking the definite integral from A to B of the function f of x, and then we have dx at the end there. So all of this notation together tells me to look at the area below the function f of x and above the x-axis from A to B. So what a picture could look like is if I kind of drew my x and y axis, and then I'm just going to draw some abstract f of x. If we have some interval A to B, if I'm taking the definite integral from A to B of f of x dx, then what we're doing is we're starting our interval at A, we're ending the interval at B, and this definite integral is going to calculate the area under the curve and above the x-axis. All right, so let's look at this in a few different scenarios here. So in this first case, we have a graph shows y equals r of t, which is showing the number of calls made per hour on a Tuesday. Approximately how many calls were made between 9 p.m. and 11 p.m. So what we're looking for is the cumulative number of calls, and that cumulative number of calls is coming from the area under the curve. So we're interested in this area under this curve r of t from 9 to 11. So to express this as a definite integral, we're taking an integral from 9 to 11 of our function r of t, and then this would be dt at the end there, since t is our input variable. So we don't have the function r of t. We also haven't talked about how to actually evaluate these integrals yet. That'll be next week. So without that, in terms of finding the area under the curve, what we're going to do is use a Riemann sum. So with that, what we can do is kind of choose which type we want to do. Let's say we'll do left endpoint, Riemann sum, and two kind of, if I'm looking at this, like 2 rectangles isn't quite enough. Let's do 4 rectangles. So what I'm going to do is I'll have a rectangle here at 9 p.m. with that left endpoint being the height. I'm going to grab 9:30 as well, 10 o'clock, 10:30. So the output at 9 p.m. is going to set the height there. The width of these rectangles is going to be 0.5, because that's like a 9.5, 10, 10.5, 11, instead of saying 9:30, 10:30. And let's see, so that height there is pretty much at 100. So one of our rectangles is a 0.5 times 100. And then we're going to add on 0.5 times the height at 9:30, which we're just going to have to estimate as best we can. Let's say 130, just about. And then I'm going to go plus 0.5 times the height at 10 p.m., which let's say that's 170. I'm really estimating here. We could change that a bit. Okay, and then the last height is at 10:30 p.m., which is just below 200. Let's say 290. 190, sorry about that. All right, then what we'll do is go ahead and add those up. So put these in a calculator. and we'll get 295 total calls between 9 p.m. and 11 p.m. Okay, so this kind of idea of cumulative, adding up this total number of calls where they were just measuring calls per each hour. If we're adding those up, it would be about 295. Okay, so for this next one, what we have is they're giving us this integral from 1 to 3 of 1 to x dx. So what we want to do here is our function is 1 plus x, so that's what we want to graph. So that is a linear function at 1 and then with a slope of 1 as well. So I'm graphing 1 plus x, so that would be our function. And then our interval is going from 1 to 3. So I'm going to look at x equals 1, x equals 3. And then what we're doing is this notation, so because it's an integral for from 1 to 3, what we're doing is we're taking the area under the curve. So what we're ending up with here is a trapezoid. This one's pretty nice to just count up the number of squares. So 1, 2, 3, 4, 5, half and half is 6. So the area under the curve is 6 square units. Okay, last one here, not last one, 2 more. So with the table, so we have this table that's estimating the total population of this town from 1970 to 2000, and we have information from 1970, 1980, 1990, and 2000. So what we're doing here is we're basically, in a way, we could say we're finding the integral from 1970 to 2000 for this function r of t dt. So we want to find this total population growth, so we want to see how this has grown, which would be the area under the curve. Now, visually, this one's pretty tricky. We're not going to have a graph for it. So instead, what we can do is rely on this table and think about using the table for forming our Riemann sum. So we could choose, do we want to do a left hand or right hand, or we could do both and do a comparison. Let's go ahead and do both. So let's do the left hand one and the right hand one. Okay, so for the left-hand one, that's where our first value comes from the beginning. So we're going to use 1970, 1980, and 1990. I need to know my change in x, so we're going 1970 to 1980, which is a change in 10. Same thing from 1980 to 1990. Same to 2000, always changing by 10. So for the left hand, what we're going to do is take that change in x, so that 10 times the height at 1970, which would be 1.5. Then we're going to go plus 10 times that height at 1980, which is the 1.9, plus 10 times the height at 1990, which is 2.2. And adding those together, that should give us a 56 in terms of, and that's thousands of people. For the right-hand sum, what we would do is we would start with, again, it's kind of like reading right to left. So I'm going to use 2000, 1990, and 1980. So we're going to have 10 times the height at 1980. We're skipping over 1970. So 1.9 plus 10 times that 2.2 plus 10 times the height at 2000, which would be the 2.4. And it should be 65,000 people. So we're noticing a difference. 56 is kind of our lower bound, 65 is our upper bound. So we have this underestimate and overestimate. So we're probably somewhere in between there. So we get kind of an estimate for what that total population growth is. It could be 56,000 people to 65,000 people. All right, our last one here. Okay, so let's take a look at this bug that is starting at a location x equals 12. So at 1 p.m., it's at this location at 12. And then it walks along with the velocity v of x, which is being graphed here. So what we have here is a bug that's going 10 feet per hour from 1 p.m. to 2 p.m. So it's going at the same rate, and then starts decreasing down, and at 2:30, its velocity is 0, which means the bug has stopped. And then the bug starts going into negative velocities, which for us means that the bug started going backwards. So what this bug did is it started at a spot, traveled some distance, slowed down to a stop, and then decided to go back a bit. So we have here in terms of total distance traveled, so how far does the bug travel between 1 and 3 p.m.? We have this distance going forward and this distance going backward. So what that's going to represent is the total area under the curve. Now, this is the first time we're seeing together this area that's underneath the x-axis. And something that we're going to do in terms of integrals is treat that as a negative value. But for the sake of this first question of how far in total does the bug travel, so let's go with total distance traveled. With total distance traveled, doesn't matter if you're going forwards or backwards, you're just going to add it all together. So with that, we're just going to treat everything as positive for this piece. So what we're going to do is take some areas. So let's see, 1 to 2 p.m. with a height of 10. So we have a nice rectangle there that has an area of 10. Here we have a triangle that has a height of 10, base of a half. So we're going to have a half times 10, which is 2.5. And then underneath the x-axis, same thing, with an area of 2.5. So total distance traveled is going to come from 10 plus 2.5 plus 2.5, which is 15. So in total, the bug went 15 feet in terms of distance traveled. Now, where is the bug at 3 p.m.? Well, this is taking into account this kind of net distance covered, meaning went forward, but then we went back. So really, what's the distance of between where we started and where we ended, or where the bug started and ended? So with that, that's going to treat that area below the x-axis as negative. So in terms of an integral, what this would look like is we're looking from 1 to 3 p.m. of this function. Let's call it v of t, or was it v of x? Yeah, v of x dx. So calculating this, we would have the 10, we would add on 2.5, but then because this is kind of the net change, we're taking away that area that's below the x-axis, so we'd go minus 2.5. So in total, from beginning to end, the bug covered 10 feet. Even though in total it traveled 15 feet, this net change of taking this kind of positive velocity and negative velocity together, we get 10 feet.